There's something else I wanted to change about this. So there's too much spacing here. These head, and it's not big enough. So let's go ahead and open up the file again. We'll fix the spacing stuff. So I don't know why it's stuck in Pano there. Okay. Let's grab everything here. There's decrease the spacing as much as possible. There we go. And I feel like that would make just everything bigger generally, but let's make these, sorry, hit the wrong one. Let's make it, it says small, but it's not small. Let's make them large. Large and in charge. Oops. Yeah, text large. So do it to all these. Can I just bam, bam? Yeah. Select them all. And do this large. Okay. So this thing seems, yeah, let's go ahead and align everything. Can I do that? Column wise? Yeah. So then I go down here and say, hey, you're gonna align like that. And then learning objective needs to be even bigger. So I'll make that extra large. And then we're gonna align everything here. Say not text. Center like that. And then finally these guys down here. I'm gonna align you as well. Yeah. And then we can kind of decrease the spacing a little bit, like in between languages in general. I feel like that can go up here, and maybe general and performance, AIML. Let's bump them all up. Compilers. Okay. So that leaves distributed systems just hanging out down here. I don't like this being called objectives. I guess it's fine. Let's bump this thing up too. We're gonna make that extra large and recenter it on July. There we go. Okay, so that's the new deal here. And then should I even include this schedule header here? I guess we can. Just bump it up here. Yeah, I think that'll do fine. We'll just call it schedule. 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 Seems, looks wrong. Schedule. Guess it's right. No worse at spelling. Okay, put it there. This guy's extra large already, right? Oops. Yeah, he's extra large already. So they're gonna have to be aligned with each other, right? Bam. Okay. So let's go ahead and hit save to, disk, this guy, replace. Then we'll delete this stuff for now. We'll bring it back later and say, hey, I'm gonna save to, export image, dark mode, SVG, this will be objectives dark, replace, disable, SVG, objectives light, replace, and then we'll undo, oops, can't undo that, so now we say open again, load from file, this, zoom out, oop, went all the way down here. Alright, so we can delete this stuff safely, and then, oops, there we go. File, export image, SVG. This is light mode, schedule 1 light, replace, schedule 1 dark, replace. And then we undo that. No, it doesn't work, so you have to reopen this thing. Go over here. Still gonna delete all this, but now we're gonna delete the left side, which will be pretty much all that, including travel. Now we say file, export image, SVG, schedule 2 dark, replace, check that, SVG, schedule 2 light, replace. Okay, and then here we can just say, hey, reset the canvas, confirm, bam, get status, get, oh, interesting. I mean, I didn't touch his timeline, but it's funny that I exported all the images and they came out identical. That means that Excalibur is pretty good at doing consistent builds, consistent exports, I guess. Okay, get CIM, update, learning objectives, what would you call this? Diagram? Get push all. Okay, refresh. Before, after. It looks a little cramped, not gonna lie. I feel like it's a bit redundant here, given that we can do headlines in Markdown. The spacing here doesn't match up there. If I select these images, it's probably fine. And I kind of want to rename this to be areas of focus. But I can do that another day. Alright, so I do need to get some Brilliant in today, so let's get our 10 minutes of Brilliant in. Okay. I don't really want to do this function shit anymore. I want to do the computer science fundamentals. Alright, let's do it. Alright, the stable matching problem. So my understanding of stable sorting is that if two values are the same if two elements of the collection have the same value, their relative positions stay the same. So if you have two elements that have the value 5, and one is in position 2 and the other is in position 3, whichever positions they end up in the sort, they will be in the same order that they occurred in the original. So I don't know if stable matching is similar to stable sorting, but I guess we'll find out. Stable matching problem. Algorithms are important because they solve problems. One common class of problem is matching problem, like which passenger and drivers should be paired for a ride-sharing service, which advertisements should go in which spots on a web page, or which hospital each medical school graduate should attend for the residency training. The last example, medical school graduates being matched with hospitals is solved with an algorithm employed by the National Resident Matching Program. Before the NRMP, hospitals individually made offers, but fierce competition led to bad behaviors. Some hospitals pressured students to accept offers years early. Others required students to accept or reject the program on the spot before hanging up the phone. So that's like our labor market. Medical students believed that their interests would be better served by a system that made offers for all graduating medical students at the same time, but if the algorithm was ineffective, it could cause more problems. Imagine the following scenario. The national... what is it called? The national... Is it... whatever. The NRMP has assigned Preety to Atlanta General, but Preety prefers Chicago Clinic. It has also assigned Key Gen to Chicago Clinic, but Chicago Gen prefers Preety. Assuming Chicago Clinic and Preety know about each other's preferences, what will happen next? Let's see here. So Preety is in Atlanta General, and he wants to go to Chicago. Key Gen went to Chicago, but wants Preety. So Preety wants to go to Chicago, and Chicago wants Preety. Atlanta General is like, I don't really care. And assuming Key Yen doesn't care, then they should swap the two positions. Assuming Chicago Clinic and Preety know about each other's preferences, will happen next. Yeah. When Preety and Chicago Clinic flout the specified assignments, there could be cascading effects. Atlanta General is now missing a student, and Key Yen is missing a residency program. Atlanta General might not want to admit Key Yen simply because she is free. Instead, they may try to lure their next choice, Ramon, away from his assignment. If they specify match, I mean, to be honest, like, I don't know the details of this algorithm, but I actually prefer a market where employees can freely negotiate instead of being forced into compliance with some arbitrary algorithm. If the specified matching if such an algorithm that's centralized and subject to influence by centralized entities, doesn't seem right to me. I think medical professionals in general kind of get screwed over. Well, I just accidentally reset my timer. Let me reset it all the way, because I'll just add a couple minutes to it. Alright, if the specified matching has even a single hospital candidate pair who are not matched to each other but would rather be, then there could be a cascade sequence of defections for the matching. A good match is one that avoids potential chaos. This property is called stability. In a stable matching, no hospital candidate pair wants to make a deal with each other and leave their assigned partners stranded. The goal of the NRMP algorithm is to come up with a matching that is stable. and therefore robust against defections by pairs of participants. Interesting. I guess it would also involve people who just flake out and don't actually go into the residency. They don't take the offer. Just do something else with their life. Stability is a measure of the collective satisfaction of the participants, not a property of any single participant's individual happiness. Consider a new situation where this sounds very communist. We're all about collective satisfaction. It's very easy to slide into oppression when you have a centralized algorithm determining the fate of individuals. Consider a new situation with the hospitals Atlanta General and Boston Memorial and two candidates, Peretti and Kiyen. Both hospitals prefer Peretti and both candidates prefer Atlanta General. Well, Peretti wants to go to Atlanta, and Atlanta wants to hire Peretti, so they should be matched together. Kiyen's like, okay, well, there's no position at Atlanta, so I want to go to Boston. And they're like, Peretti is taken. Well, Kiyen isn't. There are two possible matchings. The one where Peretti goes to Atlanta General and Kiyen goes to Boston Memorial, which can be expressed with shorthand A to P and B to Q. And the one where the assignment goes the other way. Which matching is stable? Well, I got to go back here. So Atlanta is the top and Peretti is the top. So Atlanta to Peretti, Boston to Q. Let's say that one. The matching A to P and B to Q gives both Atlanta General and Peretti their top choice, so neither will be willing to participate in a defection attempt. Therefore, this matching is stable even though it leaves Boston Memorial and Kiyen unhappy. Stability does not mean every participant gets their top choice. Such an ideal outcome may not be possible. Stability only means that no pair of participants can do better for themselves by making alternative arrangements. The next several puzzles will all involve three hospitals, Atlanta General, Boston Memorial, and Chicago Clinic, and three candidates, Peretti, Kiyen, and Ramon. Each hospital has one residency open, for which they have ranked all the candidates. Meanwhile, the candidates have ranked the three hospitals. Okay. Suppose the matching APBQCR has been specified. Which pair will defect from their current partners in favor of each other? So he wants Peretti. Okay, Peretti wants Chicago. Chicago wants Ramon. I feel like drawing a graph here. So Peretti's top two is top number one in Atlanta and Boston, but Peretti wants to go to Chicago, but Chicago wants Ramon and Kiyen. So Boston, well, this one, Boston prefers Peretti, and it's his number two. Chicago prefers Ramon. Yeah, so I would say Boston and Peretti would defect. Because she's happy. She got Boston. Atlanta's happy, got Peretti. So happy. This guy wants Boston, but he's number two. So this guy's unhappy, and this guy is not happy. Because he got his last choice, and he got his last choice. But Peretti is this main choice for Boston, so I think Peretti and Boston would defect. Matching APBQCR is not stable because Boston Memorial and Peretti prefer each other to their assigned partners. It is important to remember that both sides have to agree in order to make the switch. Although Ramon prefers Atlanta to Chicago, Atlanta would not agree to a defection because Atlanta ranks Ramon last. Similarly, Kien prefers Boston to with Atlanta and Chicago, so Kien will not agree to a defection with either of them. Consider a different specified matching with all the same rankings. Okay, so Peretti now is half happy or mid happy because he got Boston. Boston's happy. Atlanta is half happy. Kien is not happy. She's not happy. And then Chicago wants Ramon. So Chicago's happy. Happy. I gotta do a little table here because it's hard to keep this all in my head. So we got, hey, Atlanta wants Peretti but got Kien. So we'll say M for meh. Peretti is angry because she got, oh no, she's meh as well. Boston is happy because Boston got Peretti. So happy for Boston. Kien, she's the one that's angry because she got Atlanta, which is her last choice. And then Chicago here, you have Ramon, so they're happy. And Ramon got Chicago, so he's angry as well. So the problem is that like all three of these hospitals are all happy or meh, whereas the candidates are meh or angry. So the only one that might defect is Atlanta, and Atlanta wants Peretti but cannot get Peretti because they're the third choice. So they're not going to defect from Kien, so this is stable. All right, matching AQBPCR is stable even though Kien and Ramon both have their last choices. What happens if Kien tries to leave Atlanta General in favor of Boston Memorial? Well, Boston prefers Peretti or Chicago Clinic. Boston prefers Peretti and won't take her. Chicago prefers Ramon and won't take her. So both Boston and Chicago prefer their current partners to Kien, so they will not agree to the switch. Yeah. So this is really a great example of how oppressive these algorithms are. None of the candidates are happy. All of the institutions are happy. I would argue this is not a good solution because the institutions that hold power are all happy or meh. So they're all on positive or neutral side. And all the fucking people who are doing the labor are angry or meh. Just because it's stable doesn't mean that it's a good solution to the problem. I don't like this idea of assigning residencies to their hospitals. All right, 10 minutes up. Matching AQBPCR is stable even though some participants were matched to their last choice. This is okay. No, it's not. Remember, stability does not guarantee an individual participant will be happy. So why is that something you want to pursue then? The matching you just saw, A, Q, B, P, C, R is stable. Is it the only stable matching? Well, no, probably not. Let's try to come up with another one without looking at the answers. And I'll track this again as another thing here. Okay. So what's another matching here that we could do? I guess Atlanta could go with Peretti, and Ramon here. Kian, now they're angry, so let's copy this. Happy, angry. Peretti would be at Atlanta, angry. This is not going to be a good result. Kian is now at Boston. Peretti, Ramon, Boston. So she should be at Boston. She's happy. Well, these two people are angry and they'll defect. Yeah. Okay. Let's try another one. So let's do it by the candidate's preferences. So first, Chicago is not competed on for top position. So Peretti gets Chicago and it's happy. Now both candidates Kian and Ramon want Boston, but Boston wants Ramon more than Kian. So that would put Ramon with Boston and Peretti with Chicago. Boston would make him happy as well. So we got Chicago. Chicago gets Peretti, they're angry. Ramon here got Boston. Boston's like meh. And then Kian, of course, has to go with Atlanta because Chicago and Boston are taken. So she's angry. Atlanta got Kian and they're like meh. So that's probably not stable as well. So if Kian wanted to defect and go to Boston or Chicago, Chicago is upset. So she would be able to defect. I think it's the only stable matching. But let's look at these other counter examples. So AR, let's plot these out. Oops. Okay. So Atlanta to Ramon, angry. Ramon is meh. So not off to a good start here. Boston to P. So Boston's happy. And Peretti is meh. And finally C and Q. Chicago to Kian. So Chicago's meh. And so you got this angry Atlanta up here who would rather have Peretti, but Atlanta's at the bottom of Peretti, so that they're not going to be making a change there. Atlanta could go to here, but that won't work. And then Ramon would prefer to go to Atlanta over Chicago. Sorry, he's meh. He's already with Atlanta. So, yeah. These other candidates, because Atlanta's at the bottom of the barrel, it doesn't matter that it's angry. Because although they got their last pick, This is the best that they can do, according to the right-hand side's choices. Now Boston, the best that they can do, they're happy because they got Peretti. So they got their top candidate. Now Peretti's like, meh, I'll switch up to Chicago. Chicago doesn't want Peretti, so that doesn't work. Kian's like, meh, I'll switch up to Boston. Boston doesn't want Kian. And then finally, this guy is in Atlanta. He's like, oh, I'll switch up to Boston. So he wants to go to Boston now. He's in Atlanta. He wants to go to Boston. Who is Boston again? Peretti. Boston doesn't want to make a change. So I'd say this one is stable. The matching AR BPCQ is another stable matching. You can check this by looking at all potential defections. Both Peretti and Kian like their assigned hospitals better than Atlanta General, so Atlanta General cannot find anyone to defect with. Boston Memorial got their top choice, so Boston Memorial will not defect with anyone. The Chicago Clinic prefers Ramon to their partner Kian. Ramon ranks Chicago Clinic last, so Chicago Clinic cannot be involved in the defection. Since any defection requires at least one hospital, there can be no defections and the matching is stable. This example shows that there can be more than one stable matching. The NRMP solves a real-world problem by using an algorithm to assign residency candidates to hospitals, taking all participants' preferences into account. Stability is a property that guarantees that individual participants are motivated to accept the matching proposed by the algorithm. The hospital student matching problem turns out to always have a stable solution. And the rest of this chapter will work towards an algorithm that actually finds stable matchings. I only got 33? It's kind of silly. The stuff that is more difficult material for learning gives you a lower XP. Anyways, so that's about 7, 10, I'd say 20 minutes we spent on Brilliant here. So that's enough for today. Just want to keep my streak alive. Sometimes I like doing Brilliant on my downtime, but lately I don't really care for it. So let's do 20 here. Okay, I think I need to fix the conditional formatting here. So let's make this full screen. This is what range? This one here. And I think what we need to do is say, hey, this should be max value. This should be number 10. And that should be green. Like that. There we go. Save. Close that out. And then I kind of want to do a little bit better than that did. I can go up to 2 on this one now. And I'll probably get a third one in today, depending on my energy levels. Okay. Alright, we are working on chapter 2 now. Resuming reading on that. Let's do that. Okay. I think we left off on relocatable code. Yeah. Relocatable code injection based binary patching. Relocatable code injection is a technique that hackers, virus writers, or anyone who wants to modify the code in a binary may utilize as a way to relink a binary after it's already been compiled and linked into an executable. That is, you can inject an object file into an executable, update the executable symbol table to reflect newly inserted functionality, and perform the necessary relocations on the injected object code so that it becomes part of the executable. Okay. A complicated virus might use this technique rather than just appending position-independent code. This technique requires making... okay. This technique requires making room in the target executable to inject the code, followed by applying the relocations. We will cover binary infection and code injection more thoroughly in Chapter 4, ELF virus technology, Linux Unix viruses. As mentioned in Chapter 1, the Linux environment and its tools, there's an amazing tool called ERESI, which is capable of relocatable code injection. I also designed a custom reverse engineering tool for ELF, namely Krinya. It's very old, but can be found at BitLackey's. It's terrible. Krinya has many features and capabilities, and one of them is to inject object code into an executable. This can be very useful for patching a binary by hijacking a given function. Krinya is only a prototype and was never developed to the extent that the ERESI project was. Check out ERESI. Let's call it ERI project. ELF shell. Okay. So why are we talking about this tool? Need some more light in here. Okay. I'm only using it as an example because I'm more familiar with it. However, I will say that for more reliable results, it may be desirable to either use ERESI or write your own tooling. Let us pretend we are an attacker and we want to infect a 32-bit program that calls puts to print hello world. Our goal is to hijack puts so that it calls evil puts. Well, I think you would just modify the global offset table of libc to do that. So we got this evil puts function. So evil puts returns an integer, so it has the same return, but it takes no arguments. And we just call underscore right to file61 haha puts has been hijacked. And then you have the underscore right, fd, buffer, and count. In which case we do a long ret. And I'm going to have to try to learn this ASM volatile. Let's just go ahead and compile it. It's the easiest way to get to know it. So in here we'll say evil puts.c pound include syscall .h, and then we have int underscore right, takes it in a int fd, a void star buff, and an int count. And so we're going to say, hey, long ret, return -1. And then in here we have ASM, volatile, if ret is greater than or equal to 0, then return int ret. There you go. And then in here, I'm going to break this up. And we're going to say, okay, we got our first part. We should push long escaped EBX. Then we got a mov, and then we got an interrupt. Mov L ESI into EBX. And then an int 0x80, which I think is just a software interrupt. And then I need to do my, and I think I can put a space here. I don't think I need to have them crammed together. And is that a, I think that is a, yeah, percent EBX. So we push EBX, which is callee saved, onto the stack. And then, and this is all one literal, by the way, or all one string, because the literals get concatenated. So we push our EBX onto the stack, which is callee saved, and then move the ESI into EBX. And if we get out our 32-bit calling convention x86 registers. If you look at EBX base, okay. This call lead save is often used as a base pointer. Let's go to AI and say, hey, in x8632 are all args passed on the stack? I guess it's a syscall. And then we also have a pop L EBX. I don't like that they reformatted that. Pop L EBX. And then we have a colon equals A ret. I don't know the syntax really. Colon equals A, and then we say ret, and then colon 0 is sys right and colon, sorry, not colon, S is long FD, C, we didn't know how this shit works. C is long buff, and D is long count. See, I don't understand this at all. Let's do a new chat. Maybe the equals A is what is the AT&T. This is GCC inline assembly in AT&T syntax for 32-bit x86, making a Linux syscall write via int 80. Let's go line by line and also decode the constraint section. So I understand this is storing off EBX. We're moving ESI into EBX. ESI was the first argument, right? Or no, it's source index. Oh, so maybe that's S would be source index. So FD gets put into EBX. That doesn't make sense. I would expect the buffer to go into EBX, and then we int 80, which is a syscall basically. But how do we write the syscall into the register to make the kernel do the right thing? But yeah, this is stack discipline to push EBX and pop it because it's callee saved. And then this stuff I don't understand. This instruction I don't understand, and I understand what this is obviously, but I don't understand why we didn't assign syswrite before this. But yeah, let's continue with the explanation here. So we have ASM volatile, and then you have all of your statements, all of your outputs, and all of your inputs. So output is ret, and then these are the inputs. So syswrite, FD, the buffer, and the count are all inputs. Okay. All right, I'm starting to learn the syntax a little bit here. GC inline assembly is ASM. Volatile prevents the compiler from optimizing it away or reordering it. Assembly instructions, save EBX. Push L EBX. Push EBX on stack. Why? Because EBX is callee save. This is via ABI. GC expected to be served across inline ASM unless told otherwise. Move ESI into EBX. Copies the file descriptor FD into EBX. That makes sense because you're getting that from the call here. ESI is wait a minute. I thought the calling convention passed all arguments on the stack. Okay. Why? EBX is arg1 for the calling convention. EAX, ECX, EGX. Okay, they just go A, B, C, D right down the line here. Yep. How does that work? I don't understand that. We use the operands zeros register. Is that because write is the value 0? If I go to definition here, syswrite is not declared. Oh, it's lowercase right. Okay. Let's go over here. Right is 4. Okay. Okay, let's continue deciphering it. So it's pretty cryptic, I have to admit. But this line is super important. This is the inputs line. And it says whatever register is being used for the output, which is EAX, right into the register that at the beginning, write in the value syswrite. If we go to definition on that, that ends in some header file, but the compiler, I think, or something knows that there's a value 4 for this architecture. I don't know exactly how that is figured out, but it is. Anyways, so that's for this first statement, or part of the statement for the outputs, or for the inputs, sorry. I wonder why they do like outputs inputs instead of inputs outputs. I figured it'd be reverse, but this is saying take ESX, I believe. S is ESX. Or ESI. This is ESI, which again gets moved over to here into EBX. And they do that because put the FD into a register that's caller saved, and then we can move it into callee saved after we save it off. And then C here is ECX and then EDX. So they could do like A, B, C, D, but that would break the calling convention because we're clobbering over EBX and we're not restoring it. So you have to do this thing where you put in ESI and then move it into EBX. Yeah, and then the equal sign, what does the equal sign mean again? I know A, I don't quite know what A is, to be honest. Equal or A, even though I read it. Equal means output, but we already know that that's the output. Maybe I can reorder these and put the output down below. Stored in register EAX. Okay, that makes sense. So everything makes sense. These strings are just like single characters that represent a register or a class of registers, probably like EAX, AX, RAX. Like all of those will be represented by the A. Okay, it's a bit of weird syntax. Where is all of this underscore ASM syntax documented? Is it standard? Are there any standard ASM syntaxes? For C? Oh, you can just say ASM instead of underscore ASM. Okay. That's to be compliant with standards. Alright, I'm hopping off here. I'm dozing off. I'm gonna take a nap. But yeah, I wrote out the definition that he has for this program, and I tried to understand it. Because it has a lot of inline assembly, and I think I have a pretty good understanding for it. But yeah, the more I read about this stuff, the more I want to like doze off. So I'm just gonna take a break here and take a nap, and I'll be on this evening. Cool.